friends, in this video we are going to study the most famous Wheatstone Bridge, which is used for the measurement of medium resistances. Medium resistances are those resistances which are of the value greater than 1 ohm but less than 100 kilo ohms. So those resistances which are between this range 1 ohm to 100 kilo ohms, they are categorized as medium resistances. So here we will study the Wheatstone Bridge method, which is used for the measurement of such medium resistances. So let us start with our topic. The Wheatstone Bridge method, it is named after the scientist who discovered it, that is Wheatstone, and this is the most simplest and the most basic bridge network. This Wheatstone Bridge, it consists of 4 arms, and in the 4 arms we have the 4 resistances, and these 4 resistances are termed as P, Q, R and S. P and Q, they are the resistances, means known resistances are there, and R is the unknown resistance whose value we want to find out with the help of the Wheatstone Bridge, and S is the variable standard resistance. So let us first see the circuit of this Wheatstone Bridge network. So this is the basic circuit of the Wheatstone Bridge. In this bridge, you can see that we are having the 4 arms. The 4 arms are AB, BC, CD and DA. In these 4 arms, we have the 4 resistances P, Q, R and S. This is the basic designation of all the resistances. Out of these 4 resistances, the P and the Q resistances, they are the known resistances. Means the value of these resistances we already know. Okay. And these arms, that is AD and the DC arms, they are known as the ratio arms. The arms in which P and the Q resistances are connected, these arms are termed as ratio arms. In this AB arm, we have the unknown resistance R, means the resistance whose value we want to determine with the help of this Wheatstone Bridge, that will be connected in the AB arm. Next, we have the BC arm in which a standard resistance is connected. And this standard resistance is a variable resistance. Means we can vary the value of this standard resistance according to our needs or according to our requirement. Now, in between the points D and B, a galvanometer G is connected. So G here is the galvanometer. Now, galvanometer, it measures the potential difference between 2 points. So here this galvanometer is measuring the potential difference between the points D and B. Okay, and this galvanometer is used to obtain the null deflection, or we can say that this galvanometer is used for balancing the bridge network. Then an EMF or a battery battery is connected, which is providing the EMF E between the points A and C. So battery is connected between points A and C of EMF E. So E is the total voltage which is between the points A and C. Now voltage drop between A and D is E1, between D and C is E3, between AB points is E2, and between the points BC is E4. Now the total current flowing in the circuit is I, and this is divided into I1, I2, then I3, and then I4. Okay. Now the working principle of this Wheatstone bridge is based on the null deflection. This principle, that is null deflection, it says that if we vary a parameter until we got the null deflection, or until this galvanometer shows 0, then we are going to use a mathematical relationship which will be between the unknown variable and the known variables. So what we are doing here, we are varying the parameter. Like here we will vary the standard resistance such that we get a null deflection in this galvanometer. Now when this galvanometer, it will shows null deflection, it means null deflection means that galvanometer is showing 0. Okay, when the galvanometer shows 0, it means no current is flowing between this arm C and between the D and the B points, or we can say that B and D, they are same potential. When they are at same potential means there is no potential difference, so galvanometer will indicate 0. So at that point, the potential drop between the points AD and the points AB, it will be equal. Okay, because D and B, they are at the same potential. Also we can say that at that time we can define a relationship, or we can derive a mathematical relationship between the known variables, that is P, Q and S, and the unknown variable R. Okay, so that is the working principle, or the principle of null deflection, on the basis of which this Wheatstone bridge works. So what this null deflection principle says, that we are going to vary a parameter until the detector, that is the galvanometer, it shows 0 null deflection, and then use a mathematical relationship which is between the unknown and the known variables. Now here what we are varying, because the principle says that we have to vary a parameter until the galvanometer shows 0. So here standard resistance is varied. In order to obtain null deflection in the galvanometer. Null deflection means, because galvanometer, it is a deflecting type of instrument. In that instrument we will have a pointer which is going to deflect on a calibrated scale, and this scale is varying from 0 to the maximum range of that galvanometer. Now when the pointer, when no potential difference is there between the 2 points, in between that in between the points where the galvanometer is connected, suppose these are the two points, we want to find out the potential difference. So what we do, we connect the galvanometer in between. Okay, now when these 2 points they are at the same potential, then the galvanometer will indicate 0 on the calibrated scale. So when this pointer is at 0, it means the galvanometer is showing null deflection. So here in the Wheatstone Bridge, we are varying the standard resistance, where this standard resistance will have various resistance scale. Okay, first we will connect, suppose like 10 ohm, then 100 ohms. Okay, in this way we are going to vary the values of the standard resistance such that this galvanometer, it shows us the null deflection. Now, when the galvanometer shows null deflection, it means that in the bridge, in the Wheatstone Bridge, the potential difference between the points B and D, it is 0. That means B and D points, they are at the same potential. Now when 2 points they are at same potential, it means that no current is flowing between those points. Okay, so null deflection implies that no current is flowing between B and D, means no current is passing through the galvanometer and they are at same potential. Okay, so what we are going to do, as no current is flowing through this galvanometer, it means that I1 is equal to I3 and I2 is equals to I4. Also, they are at the same potential. It means that the voltage drop at the points E1 and the voltage drop, that is E2, at between the points AB, it is equal. So we can say that we have got one equation, that I1 is equals to I3. Also, I2 is equals to I4, because these points B and D, they are at same potential. Again, we can say that the potential drop E1 is equals to E2 and E3 is equals to E4. Now, what is the value of E1, that is voltage drop between A and D? It will be equal to the current I1 multiplied with the resistance. That is I1P is equals to I2R. Okay, so we can write the equation. If we take E1 is equals to E2, so what is the value of E1? I1 into P, and what is the value of E2? This is I2 into R. Okay. Now what we have written first, that I1 is equals to I3, and also we have written I2 is equals to I4. Okay. Now what is the value of I1? We know the Ohm's law, V equals to IR, so I will be equals to V by R. So V is what? If we see in that figure of the Wheatstone Bridge, we want to find out the value of I1. So I1 will be the total voltage drop upon the total resistance, because this D point, it is inactive, because this galvanometer, we will treat it as like it's a short circuit, or we can say that no current is flowing through this. Sorry, we can treat it as an open circuit. Okay, so P and Q, they will be connected in series. So total resistance will be P plus Q, and total voltage drop is that which is provided by the battery. So here we can write the value of I1 as, or I3 as, E upon P plus Q, and the value of I2 and I4, we can write it as E upon R plus S. Because here the galvanometer, it is an open circuit, so R and S, they will be in series, and P and Q, they will be in series. So equivalent resistance will be P plus Q, and here R plus S, and total voltage drop is E. Now, putting the value of I1 in this equation and I2 in this equation, so what we will get? I1 is what? E upon P plus Q multiplied with P. Putting the value of I2, it is E upon R plus S and multiplied with R. Now E and E, they are same. They are present on both the sides. They will be cancelled. So we will get P upon P plus Q equals to R upon R plus S. Now what we will do? We will cross multiply it. P into R plus S equal to R into P plus Q. Multiply P and R inside the bracket. We will get PR plus PS equal to PR plus QR. Now PR and PR, they are on both the sides. They will be cancelled. So what we got? PS equals to QR. Now if we take the ratios, P upon Q is equals to R upon S. This is the ratio and this is the famous balance equation of the Wheatstone Bridge. And this equation is used as a base for further bridge networks. Okay. Because Wheatstone Bridge, it is taken as the base of all the bridge networks. So all the bridges which are based on this Wheatstone Bridge, they will follow this equation. So this is the balance equation of the Wheatstone Bridge. Now through this balance equation, we can find out the value of the unknown resistance. Unknown resistance R will be equal to P upon Q into S. So this is the equation through which we can measure an unknown resistance using the Wheatstone Bridge. What we will do, we are going to balance the Wheatstone Bridge. Okay, we know the values of P, Q and the standard resistance. We are going to put those values in this equation and can easily find out the unknown resistance. So this equation, that is P upon Q equals to R by S, this is the balance equation of the Wheatstone Bridge. Means the condition when the galvanometer is showing null deflection, that means no current is flowing through the galvanometer. Now when the bridge is unbalanced, so under unbalanced condition, there will be a small amount of current that will be flowing through the galvanometer and the value of that small current can be calculated using the formula. Now here we are replacing the galvanometer by its Thevenin equivalent. And through this Thevenin equivalent, we can find out the galvanometer current. Ig is the galvanometer current and Rg is the resistance of the galvanometer. So this current is given by ETH, that is the Thevenin equivalent voltage, divided by the Thevenin equivalent resistance plus the galvanometer resistance. So through this formula, we can find out the small amount of current that is flowing through the galvanometer when the Wheatstone Bridge is unbalanced. Now, there are various types of factors due to which errors can occur in the Wheatstone Bridge. Means the value of the resistance which we are getting, that can be inaccurate if these factors affect the readings. Okay, so let us study that what are these errors in the Wheatstone Bridge. The first error is the limiting error. The percentage limiting error in the measurement of the unknown resistance will be equal to the percentage limiting errors in the resistances like P, Q and the standard resistance. So by using that formula, P upon Q equals to R upon S and R is equals to P by Q into S. So in that formula we are going to write the percentage limiting errors in the resistance P, Q and S, and through that we can calculate the percentage limiting error which has occurred in the measurement of that unknown resistance. So how we can calculate? Because here we are having the formula, the relationship between the R and P, Q and S is this. So if you want to find out the percentage limiting error in this measurement, that is the R unknown resistance, so that will be equal to the sum of the percentage limiting errors in P, Q and S. Okay, so percentage limiting error in P plus percentage limiting error in Q plus percentage limiting error in S is equal to the percentage limiting error in the unknown resistance. Okay, so that is how we can calculate the limiting error in the measurement. Now second type of error is now, when those instruments in which the P, Q, R and S, these resistances are connected and the four arms, the EMF, so due to the heating up of the elements also error will occur in the measurement, because the performance or the accuracy of the instrument decreases if the instrument is heated up for a long time. Okay, so if because temperature will increase because the instrument are continuously in use, so the resistance will change. Change in resistance will be R naught 1 plus alpha T. This is the resistance, that is the change in the resistance we can find out by RT minus R naught. Okay, RT is the temperature, is the resistance after T temperature, and R naught is the initial resistance. Alpha is the temperature coefficient of resistance and T is the temperature difference. So due to the heating of the elements, we can find out the change in the resistance through this formula. Also we can find out the power, that is I square R watt, and heat we can calculate by I square R T joules. Okay, so through this we can find out the error. So due to these I square R loss, that is the heat losses due to the heating up of the elements. So this I square R loss, they can change the resistors values by increasing the temperature. So due to that increase in temperature, there will be a change in the resistance values from the normal values. So when we are going to measure the unknown resistance, we will have inaccuracy and error will occur. Okay, so the change in resistance can be find out through this formula, and the power losses they can be, or heat I square R losses, they can be found out through these formulas. Next error is error due to the effect of the connecting leads between the resistors. The connecting leads which are connecting the four resistance P, Q, R and S, these connecting leads will also have some resistance. So that resistance value will be added in the value of the unknown resistance. So due to that, error will occur. So third type of error is due to the effect of the connecting wires and the lead resistors. So these connecting leads which is connecting the different resistances P, Q, R and S, these connecting leads, they will affect the value of the unknown resistance, because these connecting leads will also have some resistance, and that resistance will be added in the value of the unknown resistance. Now when the unknown resistance what we are measuring, it is of very low value, then the resistance due to these connecting wires, that will have a more effect on the values, because uh, the connecting leads, they are also having very low resistance value, and when we are measuring unknown resistance which is also very low value, so that will create much error or much percentage error in the measurement values. Okay. Now, fourth type of error we are having is the contact resistance error. Now, the contact resistance of the lead, it also affects the value of the unknown resistance, and this contact resistance, its value, it depends upon the cleanliness of the leads. So this contact resistances, they depends, its resistance value, it depends on the cleanliness of the contact surfaces and the pressure applied to the circuit. So by reducing them, we can reduce the value of the contact resistance, and further we can reduce the errors which have occurred due to them. So these are the factors which can produce error in the measurement through the Wheatstone bridge. So here in this video, we have studied the Wheatstone bridge method, which is used for the measurement of medium resistances. That is those resistances which are in the range from few ohms to several kilo ohms. Okay. For the measurement of resistances which are very low in their value, that cannot be measured through Wheatstone bridge, and also resistances which are of very high value, like in mega ohms, that can also be cannot measure through this Wheatstone bridge. So only the medium resistances can be measured with the help of the Wheatstone bridge method. So I hope that this topic is clear to you. Thank you.